time I forget to click that button. So as soon as I remember to click that button, I'm gonna do it. All right. So I asked this a little bit earlier, but nobody responded. How was the exam on Monday? I made some tweaks. I didn't make like major changes because I did not have time to do that. But I did make some minor changes, so at least it won't look the same as the first exam. And clarify, some of the questions too. Use the right notations, that sort of stuff. Good. We got 2 people typing. We got 3 people typing. Excellent. And then one more, we get several people. So 3 people are not several people yet. Once we get at least 4 people typing, then we have several people typing. All right. Okay. Well, I mean that's good to know. Well, it was never meant to make anyone cry or feel distressed. That was never the intention. And besides, I'm gonna grade both of them. So that's gonna be a while. That's gonna be a while because I need to use the same standard to grade both. Because some people may feel very comfortable with the first one already, and for whatever reason, they may not perform as well with the second one. So that's gonna be it's gonna be some work for me. Alrighty. So we have about 1 minute and a half to go, and what we'll do today is to go back to resolution and just kind of clarify what it means, when we say resolution. But today's focus is mostly going to be on CNF, conjunctive normal form, what it is, and how do we transform a Boolean expression into conjunctive normal form. Oh, I will. Well, I guess I have already put in the extra work because just thinking about how to throw in a little bit more variation to the exam questions. That's some effort. But it's kind of fun. That part is actually fun for me. Which to a lot of people are going like, oh no, that's fun to you. You're, something is not right about you. I get that sometimes. Well, thinking about using new questions every single semester, is work. However, I think I'm getting better at it. I'm getting the hang of it. Um, so there is it. That point ain't right. All right. Well, I'm 50 something years old, so boy, does not describe me anymore. All right, so I'm going to get started. So we are going to go back to resolution because that kind of explains why CNF is useful. So you can see in resolution, so kind of forget about the derivation for the time being. Okay, the derivation is going to be useful maybe some other time, but right now we just want to look at what we just proved in the previous class. So this is this is an implication, but the implication is always true, which means it is a very useful step. Okay, it basically means if you can find something of this pattern, it is a conjunction, and each component of the conjunction itself is a disjunction. And in the 2 disjunctions, where one disjunction has a component psi, and then the other disjunction has the negation of that psi, if all of these things match, then you can use these two, and then you can imply, just phi or rho. So that means, we are quote unquote concatenating these two, but one of those things is gone. Okay, psi which may or may not be a single variable in this form. It can be a very complex expression in this case. Psi is completely gone, and in other words, we have just made um, the expression easier. So it basically it reduces it into a disjunction that is that's simpler and without one of the components, one of the three components that we started off on the left hand side of the implication. So this is really helpful, but it does require everything to be in a specific form. In other words, resolution, as in as a rule, meaning if you start with this, we can end up with this. That only works when the left hand side is a conjunction of some kind, and in the conjunction, we have psi, which can be a single variable, can be a constant, can be whatever. But on the other side, the other component of the conjunction is another disjunction that has the negation of psi, and that is the most crucial part of when we can apply resolution. So now we're going to move on to the concept of a CNF, or a conjunctive normal form. So let's move on to CNF. And CNF is kind of interesting in the sense that if we want to use a conjunctive normal form, when we want to limit ourselves to only use conjunctive normal form, then we have to change the rules a little bit in terms of what is considered a well-formed formula. So this section here describes in a very mathematical way what is now considered a well-formed formula when we only want to use conjunctive normal form so that we can use resolution. So we can see omega 1, which is the set of operators that require only one single operand, is still here. Okay, so we still have negation as an operator. But in omega 2, where we had 4 members, now we only have one single member. We do not have conjunction anymore, and we do not have implication anymore, and we do not have if and only if or equivalent anymore. And somebody's going to say, but Tech, don't you need conjunction to have conjunctive normal form? So we're going to get to that later, okay? But for now, I'll just tell you that this omega 2 is correct, okay? We only have one single logical operator in this calculus. The third one here is to define every element in alpha is automatically ADE is ADE. A DE is what I call disjunction element. So disjunctive element is basically just an expression where everything in it, it's basically a disjunction of things. Okay, so it doesn't quite say exactly it's what a disjunction of, not at this point, but everything is a disjunction. It's a disjunction of stuff. Okay, so somebody is looking at this and go like, but that doesn't sound right. Okay, if we have P, Q, R, S, T as variables in alpha, how does P look like a disjunction? Well, that's pretty easy, right? Because you can always use the identity to make a single variable look like a disjunction. But for the time being, we'll just go ahead and say that yes, we can call a single variable a disjunction. And then the second one here is about the same. Okay, all it says is if you take anything out of alpha and you negate it, that is also considered a disjunctive element. I think I messed up. Sorry, I messed up because a disjunctive element or disjunction element is something that can participate in a disjunction. That's what it's supposed to mean, and it is by itself not a disjunction. Is that clear? Does everybody kind of get what I just said? The correction? All right, cool. All right, excellent. All right, so a disjunctive element is something that can participate in a disjunction which is not by itself considered a disjunction yet. Okay. So the last one is the one that is the most important, because this one basically says, if you give me a bunch of disjunctive elements, which I call phi I, and there are n of these, okay? So this is really just a notation to say that I have n disjunctive elements, and they are named phi 1, phi 2, all the way up to phi n. So this way I can refer to those over here. So if I have a bunch of disjunctive elements, phi 1 up to phi n, then I can say the disjunction of all of those phi 1 to phi n, that disjunction is well-formed. It's a well-formed formula. Is that part okay? Does everybody understand let me see, the fifth line or the fifth bullet of this list? And I can use an example too. I can give you an example. All right. And I'm going to guess most people want to see an example. Yep, there we go. All right, so let's go ahead and use an example. Let me go find my VI terminal. All right, so I think it is this one. Let me see. Yep, okay, that's correct. All right, so what we'll do is to define alpha first. So alpha is going to have the usual, the constants, and then we have P, Q, R, S, T, and the Greek letters. So we get phi, we get psi, and I'm getting back to using rho. Okay, so put a dollar sign here. All right, so this is how I'm going to define, alpha, which is very typical. This is how we usually do it. And then what we'll do is now to say what is considered a disjunction element, right? So basically anything from alpha is a disjunctive element. So now I can say P is a disjunctive element. Now everything except for the Greek letters, okay? Because Greek letters are only useful when we're trying to specify a transformation rule. So when we are looking at disjunctive elements, they are not going to participate in what is considered to be a disjunctive element. So the Greek letters are only useful when we try to use transformations. But in this case, because that is not what we are dealing with, so we will basically say you will ignore all the Greek letters. So P is a disjunctive element, R is a disjunctive element, and then we're going to throw in the negation of T is a disjunction element. So all of these, okay, I got a typo here. There we go. Yeah, so all of these are disjunctive elements because I got two double dollar sign. Now it's corrected. So P by itself is a disjunctive element because it's coming from alpha straight away. R is the same way, but the negation of T is also a disjunctive element because it's a negation of something coming from alpha. But once again, we are not considering the Greek letters when we are talking about what is well-formed or what can participate in a well-formed formula. And then we see some traffic here. So basically in this calculus, a well-formed formula can be that. Yes. Yep. Yep, exactly. So to apply the terminology that I used in the definition of what is considered a well-formed formula in this very specific case, we can now say phi 1 is, let's say P. We can say phi 2 is, I'm using exactly the same symbols that I have used earlier. So now we have phi 3 being the negation of T. Alright, so this is how I am giving you the phi, so phi 1, phi 2, and phi 3. So basically, phi is used as a placeholder to basically say, okay, give me a bunch of disjunctive elements, disjunction elements, and then we'll use those disjunction elements to define, a single, in this case, a single well-formed formula. So the notation that we saw earlier, which starts with a big V, and obviously I have forgotten how to type in the big V because I think it's just big V. I think it's literally just big V, but I want to be sure. So I go right click on the formula, go to show math as, and then go to tag commands. So I'm just gonna take a quick look here, and yes, it is just a big V symbol, and it looks like I need to use limits, to specify the subscript which is going under, and then also going on top. Okay, so I'm gonna type this in the other window here. Okay, or I don't need to do that actually, because all I can say, all I need to do here is to say phi1 or phi2 or okay, here's or, and then phi3 is a well-formed formula. So obviously this is still a little bit difficult to read, because we just have to kind of put back in, we got P or R or VEE, and then we have a negation of T. There we go. So are we doing okay so far? Is that what right hand side of the implication says? Okay, so let's check the right hand side. So the right hand side is just affirming that we have n phi i's, and each one is a disjunction element. That's what the left hand side is referring to, and then the right hand side is affirming that the disjunction of those terms that we defined on the left hand side of the implication, if you make a disjunction of all of those disjunction elements, then the overall disjunction itself is a well-formed formula. So Elijah is correct that this expression here, in this very specific case that we are considering only 3 disjunction elements P, R, and not T, then the disjunction of those 3 is a well-formed formula. So that is correct. Elijah's interpretation is correct. So are we good? I mean, because okay, so there's a reason why I do something like this, okay, instead of just using English words to describe it. Because this is actually, just this far away from being implementable as a programming in a programming language, okay, because I am using the structure of a loop. Every time you see for all I in 8 or 1 to n, that's a loop, okay, and every time you see a predicate, it is basically just saying, okay, give me something that meets this requirement, which is a disjunction element here. And this big or symbol here is also a loop, okay, because what it's trying to say is to say, okay, the n phi i's that are confirmed to be disjunction elements on the left hand side, let's use those here, make a huge gigantic or expression out of those things. That expression, that or expression itself, is going to be a well-formed formula. All right, so Danny typed in the text channel, so for it to be a well-formed formula in this calculus, there can be an unlimited amount of disjunctions. Well, technically, yes. You can OR P several times. Technically that is true. But when we implement the program, when we use this logic, in an actual program, we can basically say, okay, if you have P in it, you don't have to. If you have P or P, it simplifies to just P. So that simplification, or the fact that we do not want to have 2 phi i's being the same, when we apply this particular implication, is hidden. Okay, it's not explicitly stated. So to get that problem out of the way, okay, because Danny just kind of pointed out a possibility of, oh, but this way we can actually generate a because there's no limitation that these phi i's can have to be unique, right? That's kind of the problem is these do not have to be unique. So So to do that, oh, there's an easy way to fix that problem. I just have to change this notation a little bit. So instead of using, for all, I in this set here, I just have to use the phi i's, as a set. So that way, if the phi i's are in the set, that means they have to distinct. They cannot be the same. They cannot be duplicates. So there's an easy way to fix this, by changing the way I define the well-formed formula so that we cannot have an infinite number of well-formed formula. All right? Yeah, yes, I just said that, okay? So what did I just say? It is actually very significant. We do not have an infinite number of well-formed formula in this case. Because that was a problem, okay? It was a problem before, because when you have a haystack that is infinitely large and you're asked to find a needle, then it's really difficult or impossible to distinguish between the cases where the needle is actually not in the haystack or you have not found it yet, okay? Because remember, the haystack is infinitely large. Just because the needle is not in the region of the haystack that you have searched does not mean the needle is not in the haystack. But this way, the way we define a well-formed formula in this case makes it finite. Okay, it's only a set that has a finite number of elements when we consider it this way. So let's find out why that is the case. So we'll just go ahead and simplify the case when we have three English letters, because 5 is a little bit too much. It's not that is not needed in order to explain why the space is finite. So I'm going to get rid of 2 of those, at least for now. Okay, so we only have P, Q, and R as the 3 variables. So we're going to take a look at some well-formed formulae in this case. So well-formed formulae in this case would include, okay, I'm just going to give you some examples, right? So P by itself is well-formed, okay, and that's because we can have only one single phi I, okay, so that makes P by itself is well-formed already. And then obviously we can have P or Q, that's well-formed. We can have P or not Q, right? That's also well-formed. And for those of you who say, but can we have more stuff in the disjunction? The answer is yeah. I mean, we can have up to 3 items, right? So that is also well-formed. All right, so we'll address 2 kind of interesting questions first. The first one is, but what if P and not P are both in the disjunction? Well, in that case, you have just one, because you basically because you have a variable and its own negation inside a disjunction. So one of them has to be true, and as a result, that is just true itself. Okay, so that's not going to that simplifies to just true. Okay, and would 0 or 1 be a well-formed formula? Yes, so they can be a well-formed formula as well. So 1 is a well-formed formula. So that makes it a P or not P an interesting well-formed formula, because it is a well-formed formula in this definition, but at the same time it is also just 1. But psi or phi would not be a well-formed formula. Right, we don't use the Greek letters. The Greek letters do not appear in the space of well-formed formula. They're only used when we try to specify a transformation rule. Yeah, that's fine. That's cool. All right. Yeah. All right, so now we can just kind of go ahead and say, okay, what else is here, right? That is also well-formed. I mean, it is a symbol from alpha. So the question now is, all we see are disjunctions. So remember, when we want to apply resolution, we need a conjunction, right? So now the question is, what kind of transformation rule are we going to specify in this case so that the transformation rule would say exactly the same thing as resolution from the logic perspective. So now we'll take a look at that. Okay, so the so zeta in this case would consist of one single transformation rule. So the single transformation rule is going to use, once again, in the transformation rule you have to use Greek letters. So we're going to say phi, or let's see, I'm going to pick psi in this case because this is going to be consistent with the notes. And then the other element of the set on the left hand side of the transformation rule is going to say psi or rho in this case. And then we use the infer symbol. And what we end up with here is going to be just phi or rho. And that's going to be, oops, I forgot another set close. There we go. And I need one more open to begin with. There we go. Psi is, oh, it's not psi, that is correct. The negation of psi here. There we go. Thank you. Alright, so this is now the only transformation rule. If we kind of ignore the ones here that can do commutative rule and stuff like that, because here it's nice to keep everything sorted, okay, but I'm just going to ignore that and just kind of get down to the most important part of applying resolution. So the transformation rule that is representing resolution looks like this. So that means phi over here is representing a well-formed formula, which means it can be phi by itself can look like this, okay, and then psi by itself can look like this, and then we have negation of psi. But hold on a second here. If psi is not just a variable, then the negation of psi cannot exist. So because both of these expressions, they have to be well formed by themselves, so that means psi, this psi over here, it has to be a single variable because there's no other way for something and then the negation of that something to be in a disjunction. I'm gonna pause and make sure that everybody understand why phi by itself can be a disjunction, rho by itself can be a disjunction, but not psi. Okay, psi has to be a single variable in this case because of the way we define what is considered a well-formed formula. Sure. Okay. So remember, this is a pattern matching thing. So every Greek letter is a pattern matching identifier, if you will, of. So we're basically looking for something that looks like this. That is considered. I gave it a term that I just started to use, derivable. That's it. So we are looking for something that looks like this, that is derivable, and then we are looking for something that looks like this, also already classified as derivable. So we are looking for two things that are already derivable, and then you can see that between the two derivable well-formed formulae, the only part that links the two is one has to have a psi that is, psi, once again, psi is just a placeholder that is instantiated to something within the disjunction. But then on the other side, it must have the negation of psi. So the only way for this to happen is psi is a variable or a constant. It cannot, psi by itself cannot be a disjunction, cannot have an or in it, because that is not syntactically allowed by the way that we define what is considered a well-formed formula. Alright, so Elijah, oh okay, I'm just going to read the text from where I left off. So would so would P and not P be 1? Exactly. So Chris is correct. That is exactly the opposite. But we don't really care about that for now. Okay. So we'll deal with that later on. So psi has to be a variable Well, all the Greek letters are. Oh, okay, I see. Okay, so psi as a Greek letter as a schemata has to bind to a single variable because a negation of a disjunction would not be a well-formed formula. That is correct. We cannot have a well-formed formula that has the negation of a disjunction. So Elijah, I think that's what Elijah means. All right. All right, so if I were to be a little bit more complete, okay, what else is going to be in Zeta? So I can actually list, another thing that is really essential that we have to put it into the Zeta, and that one is when we have, well, there are a few that are kind of important. Um, for now, we're gonna say we'll just leave it alone like this. Okay, for now, we're gonna leave it alone like this because this is the one that is the most important. So we will just leave it alone like this, and we'll leave zeta for the time being to be quote unquote incomplete because we also need commutative law, because you have to move, because without the commutative law transformation, then only the last item can be psi and only the first item can be not psi, which is going to be a problematic thing, okay? Because that's just this is just expressing that the ordering should not be important because in the disjunction, um, um, you know the ordering of things are not important. And then Danny said, wouldn't P and not P be 0? Yes. And then P or not P be 1. That is correct. So Danny is correct about that. All right. But right now we are just focusing on resolution. Okay. We're just focusing on resolution here. So are we okay so far with resolution and what it looks like as a transformation rule? So a better way or more accurate way to say what I want to say is to say that this is an element of zeta. So this is by doing it like this, it means zeta can have other things, but this is the most important thing in zeta. The other ones are just for flipping things around and doing some simplifications, so they're not nearly as important as this one here, because this is the one that makes it important to have conjunctive normal form. All right. All right, so let me just kind of check whether you guys are getting this or not, or whether you're making the connection or not. So resolution as a logical expression looks like this. Okay, when we have a conjunction on one side, we have disjunction like this. On the other side, we have a disjunction like that. Then we can say that implies another disjunction, but the other disjunction looks like a concatenation of the first two, except it is missing one part. Okay, which is what is represented by psi in this case. As a transformation rule, it looks like this. Okay, so somebody may ask, where's the conjunction? Okay, because C and F is conjunctive normal form. Where's the conjunction of this? So I want to make sure that everybody understand that the conjunction is implicit. So that specific syntax. So resolution is basically saying, if you start with this is resolution. This is resolution itself, which is basically saying if you have two disjunctions and they're ended together, and one has a component that the other one has a negation of, then you can use then the conjunction itself implies the simplified disjunction, which looks like a concatenation of the first two, except one of the components is gone. So this is resolution. Now this, on the other hand, is resolution coded as a transformation rule when we want it to be mechanically done using a propositional calculus system. So I hope that is clear, because the logic or the semantics or the reason why it works has to do with this. But once we know that this is a nifty trick, then we code it into a transformation rule, and we make these special cases for the well-formed formula, so that this rule can work. And then Luke asked, phi or rho would be negated. Phi or rho. Nope, they're not negated. This is correct. Okay, this transformation rule is correct. The resolution inference rules takes two premises in the form of the clause A or X and B or not X, which gives the clause A or B as a conclusion. That is correct. So there's no negation of phi or rho. All right. Phi or rho, they have to be okay. So phi, rho, these two components, they have to be either a single constant or a disjunction by themselves. Because remember, this entire thing has to be a well-formed formula, and on top of being a well-formed formula, it also has to be derivable, and the same applies to this over here. It has to be a derivable, which means it implicitly it has to be well-formed to begin with. And based on the way we define what is going to be well-formed, so that means phi can only look like something like this, and rho can also can only look like something like that. It can only be a disjunction of variables or constants or negations thereof. Can resolution take another forms? Take other forms. I'm not sure what that means. Take other forms. Are you referring to the forms of what we start off with, or another form of how the transformation rule is specified? I'm just waiting for Elijah's typing here. For another pattern. I mean, the other pattern is simply to built in and say that reverse the order of these two. I mean, you can apply commutative rule to either side of to either of these expressions. Because commutative law basically just says you can switch the ordering of things. But I think that's the only thing you can kind of you can apply to have quote unquote another pattern specified. All right. All right. Excellent. All right. So I'm going to show you a trick. Because some people look at this and go like, I am not convinced. Okay. This just doesn't look right to me. Because, okay, so let's just say that um, in this specific calculus system that we have here, we can now say, oh, okay. So this is going to be good. Because let's go ahead and also specify iota, because iota is a set of well-formed formulae that are derivable by definition. So these are basically known to be true by definition. So we got the usual, and we're going to use the same example that we did the other day. So we have P implies Q, and also Q implies R as initially derivable expressions. Okay, so when you look at this and go like, okay, the first thing, this is wrong, okay, because there's no implication in omega 2. Okay, so what are we going to do? Okay, so before we get there, okay, let me take rho first, so that some people who are anxious about me taking rho at some time of the lecture can feel a little bit more relieved. And let's see, take a look. And the word for taking row is not a surprise today. It's just CNF. So but still, I'm gonna copy and paste it just in case someone mistyped that. So it's just CNF, and then I have to specify a time and then release it. Alright, so what time is it now? It's 36. I'll give you guys up to 1 o'clock to do it. So 1 p.m. And the reason why I chose 1 p.m. is because it's easy to type. Save and publish. There we go. And I'm doing some fun stuff on the side. Alright. So are we good? Taking roll. I mean, are most people done with typing in those 3 letters, all uppercase? Alright, excellent. Alright, so now we're going to get back to the syntax error that we saw. Yes, we got an A. So we're going to get back to the syntax error here because omega 2 only has disjunction. So this is not going to be okay. So what are we going to do here? What are we going to do to fix this problem? That's kind of okay. That's interesting. So I will tell you guys what interesting I was doing, a little bit earlier. Yep, that's right. So Luke is correct that we can change P implies Q to not P or Q. Okay, so that's because that would turn it into a CNF, right? Not a CNF, but a well-formed formula that is known to be true, along with the other things in iota which are also known to be true. So if you just listen carefully, I said one thing that is an answer to the earlier question, because I said that makes not P or Q a well-formed formula that is known to be true, along with the other things that are also known to be true. That is conjunction. In other words, everything in iota, they are all ANDed together to specify, what things are true, because the conjunction of everything, of all the elements of iota, is itself a conjunction, and that is true. So I think that is important, okay, because it is not spelled out. The conjunction is not spelled out, but it is implied by what iota means in this case. So any questions about that? Because I believe that is actually one of the important concepts, of where's the conjunction? The conjunction is implied. All of the derivables are a part of a gigantic conjunction. So the question is, where's the conjunction, right? The comma is not a conjunction. It's the concept that makes everything a conjunction. So when you look at iota, iota is everything that is known to be true, right? So are we saying that 1 is true, not 0, or not 0 is true, or P implies Q is true, or Q implies R is true? Or are we really saying 1 is true, so is the negation of 0, so is P implies Q, so is Q implies R? Is it the former or is it the latter? Exactly. So it was the latter, right? So that's what I was trying to say is everything that is quote unquote derivable, they are all ANDed together in a gigantic conjunction, and that conjunction is true. So that is implicit, okay, because it was never really stated syntactically that they're all ANDed together, but the semantics, which is basically what does iota mean, and what does derivable mean, that is basically saying everything that is derivable, they're all just a part of a gigantic conjunction. So there we go. That's how we got the conjunction, the CNF, the C of the CNF. All right, so let's go ahead and fix the problem that I mentioned earlier, which is basically saying we are not supposed to have imply here. So we're going to turn it into a negation with an or, and the same thing on the other side. So this one was pretty easy to convert. There will be other ones where you go like, okay, this one looks a little bit complicated, but this one is super easy, right? So now we're all good, aren't we? Look at this. We're all good. So now the question is, given this is our iota, in other words, all of these things are considered to be derivable, can we apply resolution? And we can just go ahead and assume commutative law is implied. Okay, so we can switch order of things, without worrying about which rule of transformation are we using. So if we just kind of ignore that, can we apply this transformation rule? And if so, who's going to be phi, who's going to be psi, and who's going to be rho? All right, so let me take a look at the text channel. I just heard a beep. Phi is okay. So let's check it out. Okay, so we are looking for two well-formed formulae, both being derivable, and they must have this specific pattern. Okay, so we have to have some phi here, and phi by itself can be a disjunction, can be a single variable, can even be a constant. Okay, and then we have psi over here. But whatever this psi is, we need that psi to be negated in the other derivable well-formed formula on the other side. So when we look at the only two things that looks like a disjunction, now all of the other ones can be seen as a disjunction. It's just going to be quite silly to turn those into disjunctions at this point, but we'll deal with that later. But of the two actually important disjunctions, look at these two. The question is, can we somehow fit these two into these two patterns over here? And if so, who is going to be phi, who's going to be psi, and who's going to be rho? That's the question. So let's. I'm going to wait for you guys to contribute the answer, but I'm going to give you the format here. Okay, so we'll start with phi is going to be blah, and then we have psi is going to be blah, and then we have rho being something else. All right, so now the question is, how are we going to instantiate the Greek letters in this case so that we can fire the rule that we have just come up with? All right, so Danny said phi can be not p. Okay, so let's try that, right? So this is the negation of p, and psi is just q by itself, and then rho is r. Okay, so let's check whether that's going to work or not. Okay, so on one side, are we getting not p or q on one side? And the answer is yep, not p or q is indeed in iota. So everything in iota is derivable by definition. Okay, so we got the first pattern in the set. Now we look at the second pattern in the set. So since we use q to instantiate psi, so that means we have not q or, and then rho is r. So do we have not q or rho or r? And the answer is yes. Okay, so Danny has the right answer. Yay! And wait, hold on, I can do this. Yay! All right. So given that, okay, so given there is a way that we can find a derivable of this pattern, and there's another derivable with this pattern here, we have just met the requirement in order to say, yes, let's go ahead and fire this rule so that we can end up with a new expression that is also now known as derivable, right? So the new expression only involves phi or rho, okay? So the new expression, I shouldn't say new because that's okay. Now we know this is also derivable because we fire the rule, right? So what is now to be known as derivable? So I'm going to start with the symbol being used in the rule itself, which is to say phi or rho. And then we're going to instantiate those Greek letters with what we found as a pattern that can basically match the two derivables in the set of the left hand side of the transformation rule. So now we say, oh, so if we make phi not p, okay, so we have not p over here, and if we use r as rho, then that is now known to be derivable. So there we go. So we started off with these two expressions that are in iota. They are by definition derivable. Now we end up with another expression that is also now known as derivable. So are we good so far? Is this example kind of working out so that you guys can see how resolution as a syntactic rule is actually applied? Excellent. All right. Very good. Okay, so because this is important, okay, I'm trying to use examples to illustrate a more abstract concept, which is not to say the abstract concept is not important, but in our step to understand the abstract concept, going through some of these examples can be helpful. All right. Can I do another example? Let me see. That is going to be hard because now we have run out of things to resolve. For this specific example, that's all we can do. There are no other things we can resolve. Okay, so if you guys are asking for another example, I'm just trying to analyze the rationale behind asking for another example, because I might be able to address the reason for asking for another example without giving you another example, because it has to be a conceptual thing you guys are not sure about, and that is why you want to have another example to show you whether it's one way or the other way. So I want to kind of pinpoint what that is. Alright, so the question is not P or R now added to D, or is that a separate part? It is added to D. Now, D is never really quote-unquote added, but now we confirm the membership of this in D. So let me make that clear in my notes here. Okay, so this confirms not P or R is an element of D. There we go. So I think that addresses Luke's question. In other words, D has always have the same elements, and so does W. The question is, at which point can we confirm the membership of a specific element in W to be also in D? So this is how we can confirm by firing the transformation rule. We are confirming, whether we're confirming that an expression or a well-formed formula is also derivable. So that's that. But I do want to have Melvin and Chandra to ask, if possible, a question, that will help me understand um, the rationale behind asking for another example, because that usually means something is not entirely clear from this one single example, and I want to know what that is. Oh, okay, I see. Hmm. So in order to resolve this, we have to find things in iota that match the pattern of the transformation. Not iota. Well, initially, yes. Okay, so initially you only get things from iota, but as we confirm more things, as members of D, you should switch to D. Now, D is a superset of iota. Remember, iota is a subset. It's the initial membership of D. But as we fire the rules, we'll find more and more things in D. So so Elijah's question is, we really should be looking for things in the set D instead of iota, because D start with, we okay, I shouldn't say start with, but the initial members that we can confirm in D are the ones that are already in iota. It's a starting point, but as we use the rule, again and again, we'll be confirming more and more members in D, and everything that is known to be in D to begin with can then be used to instantiate both of these patterns in a set. Except in this case, this is all we can do. There's nothing else we can do in this case, if we do not count commutative variants of the same expression. All right, so okay, so Elijah is okay with that, and then Danny is asking. So it has to be in iota or D. Well, let's just say it has to be in D. In other words, that part was actually discussed in last Wednesday's lecture. So this thing, okay, has to be in D. This thing here also has to be in D, and the use of the Greek symbols is a constraint. Okay, so in other words, we are not just picking any two elements in D in order to say this rule can fire, because the constraint here is, I mean, phi and rho, they're not really much of a constraint. They're basically saying, okay, I can be anything. Not a big deal. But the psi versus the not psi, that is the constraint. In other words, whatever you pick from D to meet this pattern here, whatever you pick to meet this particular pattern in the rule, one must have a variable that is not negated, and then the other one must have the negated version of the same variable. And if that requirement is met, then we say, okay, we can fire the rule, and now we have another expression where the membership in D is confirmed. So I hope that answers Danny's question. So we are not really changing, the meaning of, what is in D, what is in W, and so on. We are actually more or less, just placing more limitations of what well-formed means in this case, so that we can focus on the rule, the one transformation that makes, the difference in this case, which is resolution. Okay, is the second part of what I said true? The second part being, not just any well-formed formula, because well-formed formula is syntactically correct. That is true, but don't necessarily have a value of true. So yes, so you have to use something that is confirmed in D in order to instantiate the patterns in the set as the left-hand side of a transformation rule. In the parentheses, and I is a subset of D. Yes, so everything in D is also, everything in I is also in D. Yes, that is also true. Yep. All right. Excellent. All right, so I think this is good, but I cannot give you, this cannot push any further. Okay, I cannot push this any further just because of the limitation. So if you want to use this example any further, I'm not sure whether it's going to help or not, because it's going to be about the same stuff. So if we just add one more item here, and we say, R, okay, right arrow implies PQRS. Okay, so we have to add another letter here. Okay, so if we are to add, right, R implies S, so obviously this has to change to not R or S, right? Because we have to make everything well formed, but they mean the same thing. So with that here, now we can say, okay, so what can we do at this point? We have just confirmed that not P or R is now confirmed to be an element of D, which means we can now use it to instantiate one side or the other of the set on the left-hand side of a transformation rule. So now we can say, oh, okay, this is kind of cool, because what we can do now is to say phi is not P, we'll say psi is R, and then we can see not psi here as not R, and then we can also just say that rho is S. So now we can fire the rule again, and I will make it very clear when I document this. So give me a second here, because I have to copy and paste this so that we can now specify how are we instantiating the Greek letters. Phi is still the same, psi is now changed to R, and then rho is now changed to S. Okay, so by instantiating the Greek letters in this specific way, we have now we have two elements in D, one matching this specific pattern and the other one matching this specific pattern, and as a result we can fire the rule, and when we fire the rule we can now conclude that not P or S is also confirmed to be in D. Okay, so I'm just gonna copy and paste this. Oops, no, not there. There. Okay, so now we can also all right, there we go. Is that helping? You can also derive not Q or S. Yes, because it's transitive, because implication is a transitive sort of thing. I'm not going to call that a relation, but it does have that transitive property to it. So Elijah is correct. So now we can instantiate things in a slightly different way, and we can say not Q or S can also be confirmed to be an element of D. Okay, so I am going to make that an exercise for you. Okay, so ungraded assignment. Okay, find another way to fire the transformation rule. Okay, so I'm going to leave it up to you guys, but the mechanics is going to be exactly the same. So is that helping? Since I was asked about another example, this is kind of the other example. Okay, so all right. Well, I think this example is specifically important because now we can confirm, and we are using something that we just derived to be a part of the left-hand side of the transformation rule. And I think that really is the significance of this specific example, because it's not just another example, because in the previous one we chose everything that was from iota, even though we know D is a superset of iota, but we picked everything that was given true to begin with. But this time we use something that was just derived, and we use it to be a part of, to be one of the components of the left-hand side of the transformation rule. So that kind of illustrates how this can kind of go on and on and on, but it cannot go on forever. Okay, the reason why it cannot go on forever is every single time you fire that rule, you lose something. Okay, the resulting expression that is confirmed to be in D, that is confirmed derivable, has one thing that is missing. So things can only get smaller and smaller, even though we are concatenating phi and rho, but things can only get smaller and smaller until, quote unquote, there's nothing left. And that's what we want to do. Is that we want to make it so that there's nothing left. So this is a good time to transition to proof by contradiction, because that's what we are trying to get to. And before we get there, I am going to state something that is rather, I would say, rather obvious at this point. So I'm going to say P is going to be the same as P or, oh, okay, bad typing on my part. Is that okay? Does everybody get this? If you give me a variable P, okay, as an expression, P or false is going to be the same thing. It doesn't change the meaning. Let me go back to the text channel because I think we got some more stuff in there. Okay. If iota has not P or not Q, Q or not R, then you would not be able. Oh, okay, yes. Then you can derive not P or not R. That is correct. So what Danny typed at 12:59 is correct. That time doesn't seem to sync with my time. I'm just looking at the time. Nope, it does not sync at all. All right, and then Danny also asked, the negation doesn't necessarily have to be the second half. That is correct. I mean, so because these two are elements in a set, that means there's no actual specific ordering between these two. They're just two things in a set, but there's no implied ordering between these two. And I already said, ordering within a disjunction, we're just too lazy to specify commutative rule in this case. So we're just going to go like, okay, if you can find, something that's not negated on this side and something that is negated but on the other side, we'll fire the rule, so that, the positioning of psi is not important. Because otherwise you just have a whole bunch of other rules to specify, the commutative rule of disjunction, which is, I mean, it's nice to have that, but we don't really need it. All right. So, okay, so there are a few things that are important. The first one is anything or 0 is the original thing. In other words, 0 is the identity with respect to disjunction, much like 0 is an identity of addition. Is everybody getting that? We can, if you give me an expression, huge and long expression or simple one, and I say that expression or false, okay, that doesn't really change anything. It just makes it a little bit longer, but it doesn't change the actual value of the expression. Are we good with that? All right. So that means implicitly, okay, so if I were to go back to the original iota, I could do something, that seemed to be pretty stupid, like this, right? Everything, I'm just gonna say, just add a or false to it, okay? That just looks silly, right? But it doesn't make it wrong. Are we good so far? That I can just kind of go like, oh, okay, since or false doesn't change the meaning in terms of semantics of a disjunction, we'll just kind of attach that or false to everything. But that means this iota means exactly the same thing as before. It just looks a little bit more awkward because yeah, but that's why would you do something like that? Okay, it's really useful. Okay, we'll get to that. All right. So I think we are okay now in terms of understanding what is resolution and how resolution as a logical step is transformed into a transformation rule, which is basically a syntactical thing. It's like, okay, let's find something that is negated on the other side and something that's non-negated on this side, and then we concatenate everything else, okay, from the two disjunctions to make a resulting disjunction, and that's going to be quote unquote derived at this point. Okay, so that's kind of one important topic. So now we're going to move on to proof by contradiction. So there are a few key pieces to this. There's also completeness of CNF. I think I will talk about proof by contradiction first, and then next Monday we'll get back to how to convert everything into a CNF. Okay, so because I think in terms of the forest, it is important to get to proof by contradiction first, and then we can get back to the itty gritty detail, which is kind of, let's just look at one pine tree in terms of the completeness of CNF. In other words, give me any Boolean expression, I can turn it into a conjunctive normal form. So we'll defer that discussion, but we'll get back to it for sure, because I have one homework assignment just for this part. So we will get back to this. So for now, we're going to get to proof by contradiction. So here is the proof that proof by contradiction is going to work. But this is not the proof itself, okay? This is a corollary, which means it is a mini theorem that says something, but by itself has very little significance, okay? So I'm not going to get through all the steps. You should probably go through the steps and understand how it is derived. But the bottom line is this implication here. Let me point out which implication. This one here. This implication is always true. Okay? So what is the bottom line? Techia, just give me the executive summary of what this means. Well, the executive summary means if you know a particular implication, like P implies Q is true. Now, in this case, P can be any expression and Q can be any expression. This is outside of the context of a propositional calculus system. So this is back to just general logic. So P can be any expression, Q can be any expression, any Boolean expression. If P implies Q is true, then, okay, because this is basically the same as then, right? Because implies is the same as then you can choose any R as an expression, okay? Pick any R as a Boolean expression. It doesn't matter which one, okay? Then we can say P and R implies Q and R. All right? So does everybody understand what this implication is trying to say? If you know that P implies Q is true, then we also know that P and R implies Q and R is going to be true regardless of what P, Q, and R may look like. Is that okay? Or are we having, do we need a discussion of what this implication means by itself? All right, okay. So the derivation, which are all of these steps here, that's basically the proof of this corollary. All right. P and anything implies Q and anything. Yep, exactly. That anything has to be the same, okay? Cannot be two different anythings. It has to be the same anything. But if you say conjunction with anything, as long as it is the same thing, then the implication still holds, as assuming P implies Q holds to begin with. All right, so this by itself is not very useful, okay? So what we're going to do is to, Danny just typed something. Is that just something we logically think through, or is it a theorem somewhere? This is what I would call a corollary, which is basically a miniature theorem. It has no name by itself that I know of. But since we can prove that this implication is always true, so that means this is now a theorem because we know it is always true based on Boolean algebra. So we don't know it's always true until we go through all those steps. That is correct. This is so when I start with this, it is a proposal. Okay, I want to see if this implication is always true, or how I can simplify this implication too. And all of these steps here are applying Boolean algebra in one way or another. Okay, so I'm exercising all the rules that we normally use in Boolean algebra. But at the end of the derivation, we end up with just a simple true here. So that means this implication is always true regardless of what P is, what Q is, and what R is. So that makes this an interesting theorem, because it says, okay, so if you give me an implication, okay, like this, and you tell me this implication is true, then I can always AND the left hand side and also ANDing the right hand side with the same additional Boolean expression, the third Boolean expression, and this implication would still be true. So why would that be useful, right? That's kind of the question. So now what we're going to do is to relate this to iota. So now let's make a conjunction of all the known to be true well-formed formulae. And I'm using psi again, but in this context, psi is not the psi in a propositional calculus system setting. So this is just me using psi as a symbol to represent the conjunction of everything that is in iota. So is that notation okay? Does everybody kind of feel comfortable that psi in this case, in this very context, is simply the conjunction of everything in iota? So give me an iota, okay? Give me a calculus, a propositional calculus system. Give me that iota, and I would just do an AND with everything in iota, and I'll call that conjunction psi. That's basically how psi is defined. So are we okay with the definition of psi? And this is not looking at it from the perspective of the transformation rule. This is looking at it from the perspective of just usual regular logic. Okay, so that's good. All right, so now we are going to use phi. And once again, this is not a part of propositional calculus. I'm just using phi as a symbol to represent a theorem that we want to prove. Okay, it is something of interest to us, and we would like to know whether the theorem is a result of psi. In other words, what we want to find out is whether psi implies phi or not. This is how we usually prove a theorem. That's basically what a theorem means. Okay, when we say that phi is a theorem, it means is it derivable from everything that is known to be true to begin with. So are we still doing okay so far? In this context, what psi is representing is just a conjunction of everything that is known to be true, and phi, on the other hand, is a particular Boolean expression that is of interest to us, and we want to know whether that is implied by everything that is known to be true. So I just want to clarify to make sure that the symbols, the meaning of these two symbols are clear at this point. All right, very good. So when you have a mathematical proof, it's basically just a long chain of implications, so that you can use a long chain of implication to link everything that was known to be true to begin with to the one thing that your professor is asking you to prove. It's just a huge, big, long link chain. I shouldn't say link, but chain of implications. All right, so now we look at this. Okay, this is what we want to do. Okay, we want to say, we want to show that psi implies phi. Okay, all right, and if you have the correct phi, this is going to be true. If you have the wrong one, it may not be true. So I can now use the corollary that we introduced earlier and say, okay, let's add something to the left hand side of the implication, and we're going to add the same thing to the right hand side of the implication. And when I said add, I meant use conjunction. Okay, so we will basically turn the left hand side into a conjunction and turn the right hand side into a conjunction, and then the additional component that we are ANDing with just has to be the same thing, right? So nothing is going to stop me from using conjunction. Okay, using the negation of phi, and remember phi is representing the theorem that we are trying to prove, but I can say let's just AND with the negation of the theorem that we are trying to prove on both sides of the implication. So this implication here is the application of the corollary that we just talked about, which is basically saying, yeah, you can just AND something on both sides, as long as you're ending the same thing on both sides, the implication still holds. So are we okay with this, the second line of this derivation here? Just where my mouse cursor is located. Okay, so this is why that corollary was important, because we needed that in order to get to here. So now we go to the next stage, which is looking at phi and not phi here. Phi and not phi, at the very beginning of this lecture, that was discussed, right? That simplifies to false. So now we can say if phi is indeed a theorem, then the conjunction of everything that is known to be true and the negation of the theorem that we want to prove, that conjunction has to imply false. All right? Are we still doing okay so far? Because from the second line to the third line is the simplification of phi and not phi being false. All right. All right. So now the question is, so what is the big deal here? Well, the big deal here is this is another way to prove a theorem. So instead of using a super long chain of implications, you can now say, okay, I'm just going to assume the theorem is not true to begin with. And if I can combine that assumption with everything that is still known to be true, and I can arrive to a conclusion of false, then I have just proven the theorem to be true. Yes, I know how confusing that sounds, but that's exactly what I am trying to say here. So in order for this implication, the one that is under the mouse cursor right now, in order for that implication to be true, what do I need the conjunction on this side? So if you look up the truth table of implication, I want the implication itself to be true, but we already know that the right-hand side is false itself. What do I need the left-hand side to be? It has to be false. Very good. Okay, so we want this conjunction to be false if I want to prove that phi is a theorem. All right. So this is interesting. This is the essence of proof by contradiction. So the next paragraph says, this means the conjunction of all elements of iota and the negation of the theorem to be proven should lead to a contradiction. In other words, it should lead to a conclusion of false. So I'm trying to, okay, we got 1 minute left. So I'm going to give you an example of proof by contradiction. It's going to be okay, I'm going to give you something that's simple, because I was about to show you the pigeonhole principle. How do we prove that the pigeonhole principle itself is valid? Okay, so I'm not going to do that. I'm going to give you a quicker and easier example. So I'll just say that I have one kind of socks in my drawer. Okay, so I've only got one kind of socks in my drawer, and how do I prove that if I pull two socks out of the drawer, it's going to be a pair? How do I use proof by contradiction to do that? So that's the challenge, and I will answer that challenge in just a little bit. I'm doing something interesting again on the side. There we go. All right, so I'm now done with the other interesting thing. So, all right, so what you do is you negate the theorem first. In other words, the theorem in this case is to say if I pull two socks from the drawer, I should get a pair. So the negation of that is I pull two socks from the drawer and it is not a pair, right? That's the negated theorem. So now I have to say, okay, how is this negated theorem going to conflict with what is known to be true? So in this case, what is known to be true? What did I tell you to begin with? I said I only got one kind of socks. That was the iota. That was one of the elements of iota, was that I only got one kind of socks. But now the negated theorem says if I pull two socks out of the drawer, I do not get a pair, which means I get two different kinds of socks. That's the contradiction, because I have two kinds of socks and I only have one kind of socks. That conjunction is false. And because the negated theorem, which is I pull two socks out of the drawer and I do not have a pair, that's the negated theorem. And because it leads to a contradiction, that means the non-negated version, the original theorem, which is I pull two socks out of the drawer, I get a pair, that has to be true. So this is one kind of wacky way of applying proof by contradiction, but you can kind of see how it sort of makes sense, right? You negate the very same thing that you're trying to prove and see what kind of crazy scenario that's going to lead you to. That's kind of what proof by contradiction is about. And there are others too. If you guys have time, you'll read the pigeonhole principle, because the pigeonhole principle is kind of like the sock example, except this one is also very, I would say, it's very sensing type. In other words, you can actually draw a picture. You can actually imagine in your head a bunch of pigeons, right? It's also very it's also very profound, because there are, to my knowledge, there's no way to prove the pigeonhole principle directly. But proof by contradiction is easy just like that. Okay, easy like pie, although today is not pie day. So proof by contradiction is a very powerful proof technique, well beyond the context of this class. But we haven't shown the connection yet, right, between proof by contradiction and resolution and CNF. So next Monday, we're going to try to combine all of those concepts, but we first have to go back to talk about how to derive the CNF first. Okay, so we will first talk about, give me any Boolean expression. It can have implication, it can have or, it can have and, it can have negation of, some and then it has negation of or, and so on and so forth. Doesn't matter. As long as it is a valid Boolean expression to begin with, I have a way to convert it into a CNF. Because without that, then CNF is useless, right? Because you can say, oh, but if CNF cannot express everything that we want to be able to express as a Boolean expression, then we cannot use this system. Okay, it has very limited application. But since we can indeed do that conversion, that makes it really, really useful. So let me go back to the text channel. The lecture is officially over. So if you want to leave now, it's perfectly okay. I'm just catching up with the text channel right now. Like, scientific studies are conducted. Assume the opposite of your hypothesis and try to prove it. If you cannot prove it, more evidence that your hypothesis is true. Not exactly the same thing, because in the case of the null hypothesis application, there can be other ways to explain it too. So it's not exactly the same, because in scientific studies, you are collecting evidence. You have to know a hypothesis. But you can only prove like one thing at a time. This one is absolute. Okay, the proof by contradiction is absolute. And then Philip said, so will resolution and proof by contradiction assignment due date be pushed back? Oh yeah, absolutely. Because we have to push back the CNF assignment. I'm not going to assign that over the weekend, because I think this weekend will be helpful if you guys just kind of try to absorb everything that I have talked about so far, because The application of the transformation rule by itself is a little bit abstract to begin with, and then resolution is also, in a way, it is not abstract. In a way, it is just a special case of a kind of transformation rule. But the way we got there is a little bit. It's a journey to get there. And now we are introducing proof by contradiction, which is going to play a very important role in what we're going to be talking about next week. So having familiarity of all the concepts that we have talked about so far individually as pieces is going to be super duper important. And that's what I'll be focusing on, studying over this weekend. All right. So no assignments, per se at this point, but you have to kind of make sure that you read the all the various sections of this particular module, and that you feel comfortable with those concepts. And if you're not comfortable with those concepts, just kind of ping me, ask questions, use the questions channel. Think of some examples and go like, what about this, right? So those would be really, really useful activities that you can do. Yes, so I am going to record another lecture, so that's a very good reminder, because it is a long weekend now, because we have until Monday before we meet again. So over the weekend, I will do a recording of another lecture because we lost one lecture time, for the makeup exam. So I'm going to have another lecture of 80 minutes recorded over the weekend. So it's going to be the midpoint between now and Monday, that I will make it available. So you guys can watch it, and it's going to be about transforming Boolean expressions into CNF. So that will be covered, using the recorded lecture. So now you can compare between a live lecture like what we're doing right now versus a recorded lecture. You can still post questions in the text channel, by the way. So I will try to answer all of those questions, in the text channel, but it's not going to be, interactive like this. Yeah, so the CNF assignment is going to be assigned on Monday, because over the weekend, probably on Friday, somewhere between Friday and Saturday, I'll give you the additional recorded lecture that will talk about how to convert something into any Boolean expression into CNF. So if I assign the CNF assignment on Monday, I think that's pretty fair because the material would have been introduced and discussed over the weekend. Alrighty. Any other questions before I sign out of the voice channel? All right. Well, if there are no questions, have a nice weekend. And if you don't see me posting something on Friday, for the makeup lecture, kind of ping me and gently nudge me and go like, "Hey, Tack, how's that recorded lecture coming along?" So I kind of need that sometimes. Yeah, have a nice weekend. I know I'm gonna have a busy weekend, right? Yeah, with a grading of the 2 exams and also a recorded lecture. That should be a fulfilling weekend, I should say. All right, so I'm gonna drop out of the voice channel now, but I'll stay on the text channel as long as there are still activities, and then I'll take a break before I go to a union meeting. Yep, you guys all have a good day, have a nice weekend, and I will see you on Monday.